Welcome everyone to today's video. We're going to talk about the temperature dependence of reaction rates. Okay. So, right, it was found initially, right, that the reaction rate constant itself is dependent upon temperature, and that they found, right, when you measure the rate constant as a function of temperature, that if you end up plotting the natural log of that rate constant versus 1 over the temperature, okay, you get a straight line. Okay, so if you plot something like this, you get a straight line, and you can always rewrite that equation here. And this is the Arrhenius equation, is what it's called, right? Named after the guy who discovered it, right? And so again, this initially was discovered and determined experimentally, right? And so then you would measure the rate constant as a function of temperature, do this type of plot, right? The y-intercept will give you that pre-exponential factor, and the slope will give you this term here, EA, okay, which is called the activation energy, right? Now, right, the shape of this Arrhenius equation can tell us some things, right? The form, right? The fact that the larger the activation energy is, the more dependent on temperature that reaction is. And we'll talk a little bit more about kind of why that is in a minute, right? But just looking at the functional form, right, as EA gets bigger, right, what that temperature is becomes more and more important, okay? Right, if that EA, that activation energy, is very small or near zero, right, there won't be much temperature dependence on that reaction, right? And A itself is just some kind of constant that we'll talk a little bit about. The units of A is just the same as the units of your rate constant. Okay, which, as we talked about before, the rate constant has kind of funky units, right? It's kind of whatever the units need to be for it to work out for the overall rate law. Okay, so the units of A, right, are just the same as the units of K, which depend on the total order of the reaction. Okay, right, and so if we know the rate constant at one temperature, we can find out the rate constant at another using kind of this equation, or we can use this equation to be able to solve for the activation energy or things like that, right? So if I say measure the rate constant at two different temperatures, okay, and I have these two different equations, okay, right, sorry, those two equations, L and K are 1 and such, right, where I have two different temperatures, T1, T2, right, take the difference between those two equations, right, I'll simplify to this functional form, which should look very familiar from things from thermodynamics, right? In thermodynamics, we talked about equilibrium, right? We had the natural log of the equilibrium constant at one temperature over another, right, is related with the enthalpy of the reaction divided by R times the difference in 1 over the temperature, right? So this is a very similar functional form as that, okay? But here we're dealing with the rate constants and activation energy instead of equilibrium constants and enthalpy. Okay. Now, some time ago, right, long after it was experimentally determined, right, empirically determined, this Arrhenius equation, right, so people came up with this theory called transition state theory, and that we'll describe, right? Okay, and right, if we're just thinking thermodynamics, right, there is no, like, this activation energy has no relevance, right, because thermodynamics just cares about what the reactants are in the products, right, and not what's in between, right? We care about what's in between, right, for kinetics, because that tells you and relates to how fast something is going to occur, right? And so that activation energy, right, is related with the lowest energy barrier, right, between reactants to products, right? So that activation energy, right, is that lowest energy barrier, right? What is the lowest energy state that is required to be able to transition from reactants to products, right? And that is related with then the transition state, right? That state that helps us transition between reactants and products, okay? And so that energy barrier is related with the activation energy, right? It's how much energy required to activate this thing to the transition state, okay? Right? Now, transition state theory itself, right, you have some random reaction coordinate. In this case, the reaction coordinate has to do with the bond distance between, say, this oxygen and carbon, right, or the oxygen and chlorine, right, or bromine, sorry, bromine, not chlorine, okay. But in general, this reaction coordinate, right, in these plots, right, can be some collective motion of your reactants and your products, right, some collective motion of the atoms in your molecules, okay, right. And so transition state theory states that there is this minimum energy barrier between between your reactants and products, okay? And in order to get to products from reactants, you have to have enough energy to overcome that barrier, okay? And then the atoms and the molecules need to be oriented correctly when they collide, right, in order to form that transition state geometry, right? You know, again, in the example in the previous slide where I have OH colliding with CH3Br, right? If the OH collides head on with, say, the Br in the CH3Br, right, then there's no reaction that's going to occur, okay? Because the oxygen is going to be hitting the Br, or say the hydrogen collides in near the carbon, still no reaction is going to occur, right? You need that oxygen to approach the carbon on the other side of where the bromine is, right? So you need the correct geometry when the reactants collide, and then you need enough energy to form that transition state, okay? And once those two criteria are met, then you can form the products, okay? And so the question is, right, is what's the probability of these things colliding in the way they are, and what's the probability of having the right energy, okay? Well, that probability of having the right energy just goes back to our Boltzmann statistics that we've talked about in Chemistry 3330, right, in the previous video, okay, where, right, the probability of having some energy, specifically the activation energy, is just given by the exponential minus beta over the activation energy divided by Q, right, where again beta is equal to 1 over Boltzmann's constant times temperature, okay, right, and so that tells me what is the probability that my reactants have that energy, right, have that activation energy, that excess energy to be able to react, okay? And so, right, right, if we compare then kind of this probability for things to react, right, or probability that they have the activation energy to be able to react, right, then we think of the rate constant as, right, how often these things collide, right, times, say, what is the probability that they collide in the right orientation, right, and we relate that to the V attempts here. So I'm gonna have this kind of rate aspect to it, right? So there's a probability that they have the energy, and then there's something times the speed in which they're colliding, okay, and colliding in the right orientation, okay? So these are kind of these two parts, right? And it's the product of these two things that give me the overall rate constant, okay? And so when I plug in for that probability with the Boltzmann distribution, right, I get this equation here, and I can compare that with the Arrhenius equation, right, and see that, okay, you know, this is where kind of that Arrhenius equation comes from, right, that this V attempts over the partition function Q, right, is related with the Arrhenius constant A, right, so the Arrhenius constant is related with that attempt frequency, right, V attempts, right, over Q, okay, and then we see where that activation energy, you know, the exponential dependence that activation energy comes from. It comes from this Boltzmann statistics, right? Right. What is, you know, it comes from the fact that that describes the probability of having that energy. Okay. Right. And so finally, when we talk about catalysts, okay, and we'll talk a little bit more about catalysts when we talk about mechanisms and things like that. But when we talk about catalysts, right, how that affects the rate of the reaction is by just lowering that activation energy, which then increases the rate constant, right? So the catalyst affects the rate constant, right? So catalyst does not, right, affect the free energy change and things like that in the reaction, right? But it will affect the rate constant and sometimes the rate law, what it looks like. But often it affects the rate constant by changing the activation energy in your reaction, okay?